Okay, kids, this is section 9.4. It is inscribed angles, and inscribed angles are like the second step to a central angle. Central angles are where you have the center of the circle, and a central angle has the vertex of the angle that's in the center. Okay, in an inscribed angle, the vertex of the circle is on the, let's see, has a vertex on the outside of the circle. So like R is the vertex here, it's on the outside of the circle. Okay, so that's inscribed versus a central angle. Central angle versus an inscribed angle. So there's a little bit of a difference between the two. Central angle has the vertex at the center. An inscribed angle has a vertex on the outside of the circle. Okay. Now there's three different ways that an inscribed angle can look. You can have one of the sides of the angle actually going through the center. So like this side of the central angle or the inscribed angle would be like the diameter. You could have the angle going around the center, or you can have it going on the opposite side of the center. Okay, so not even touching that center there. Those are three different ways that you can have inscribed angles. Now in each one of them, it does not matter which one of these you're talking about. The angle here of the inscribed angle will always be half of what this intercepted arc is. So if this arc, let's say, is 120 degrees, this angle will be 60. Okay, if this arc here is 90, this guy will be 45. This one, let's say, is 140. This guy will be 70. And let's say this one is 60 degrees. This one will be 30 degrees. So this angle in here is 30 if this arc is 60. This angle is 70 if this arc is 140. And this angle is 45 if this arc is 90. So it doesn't matter what situation you're in relative to the center, the inscribed arc will always be half. Now going back to central angles, let's say this guy was 100 degrees. The central angle right here will also be 100 degrees. So that's how central angles differ from inscribed angles. Okay, if I would draw this central angle that connects with this arc here, let's say this arc was 100 degrees. This central angle would be 100 degrees, and this guy would be 50. So it's just the difference between being connected to the center, which is half the distance to the outside, or the one that's all the way on the outside. So the central angle will be exactly the same measure as what the arc is, versus the inscribed angle will be half of that. Okay. So going down here on the first example, oh shoot, let me have you write that down. Well, let's just wait. We'll write them all down, all the theorems down at the end. So this theorem 9.6, I have them all written down. I'll show you that paper here at the end, and I'll have you write those all down. Okay. Example 1, they want us to find the measure of angle P. P is right here. Now P is made from these two segments here, and the arc that's across from it is 70. This is an inscribed angle. It's not going to the center. It's all the way across the circle. So if this one's 70, then this one's half of that, 35 degrees. Okay. All right. So angle P, 35 degrees. Okay. Arc PO, they say that we're trying to find this one, and if this guy is 56, I don't know why it says equals 60 on there. That's a typo. So cross out that equals 60. They're saying that angle N is 56 degrees. They want to know what this guy is. That guy's just going to be double him, and he is, let's see, 112 degrees is what arc PO is going to be. I don't know why that says 60 there. 112 degrees is what that arc will be. Okay, so it's just always double across from it what it is to start with. All right, and I guess the reasoning for that, if you want to know a reason, a straight line is made from 180 degrees. So like this line right here is 180 degrees, but circles are measured in 360s. So you're going from a linear measure, this would be what a line is, to a circle, which is 360 degrees. So you kind of have to double it when you're going from one to the other. Okay, so this guy you double to figure out what the arc is. Okay, this next theorem says that if I have two angles, like this guy here and this guy here, angle B and angle C, angle C is made up of these two line segments. So DA is really the arc that's opposite angle C, okay? Now, B is made from these two segments here, and DA is also the arc that's intercepting that, okay? So really angle C is opposite DA, and angle B is opposite DA. So when those two angles, angle B and angle C, when they're opposite the same arc, those two angles will have exactly the same measure, okay? So if angle C is, let's say, 40 degrees, angle B will also be 40 degrees, okay? Because they intercept that same arc there, okay? So that leads us to this example down here. So we have angle T is represented by 3x minus 5, and T is made from these two line segments here. So SV is the arc that makes up what angle T is. Angle U is 2x plus 15, and angle U is made from these two line segments, so that's also intercepting arc SV. So since those two make up the same arc, this angle here and this angle here will be exactly the same measure. So 3x minus 5 will be equal to 2x plus 15. Okay, and then if I do the algebra, if I subtract 2x, x minus 5 will be equal to 15, and I add 5, so x is 20. And they want us to find the measure of angle T. So if x is 20, 3 times 20 minus 5, 3 times 20 is 60, 60 minus 5 is 55. So angle T is 55, but then that means angle U is also 55. Okay. So either one, I could have plugged this 20 into the 2x plus 15 and it would have been the same as well. Okay? So those are two angles inscribed by the same arc. All right, on to the back side. They give us a proof, and they want us to prove that these two triangles are exactly the same, okay? And we have kind of 4 different ways of proving that triangles are the same or are congruent to each other. There's side, 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 angle, side, angle, side, angle, and angle, angle, side. So we're going to use one of those methods to prove that these two triangles are congruent, okay? So they give to us, given is that JM, this guy right here, and KL, that those two guys are exactly the same. So I'm going to put a tick mark there. Those two guys are the same measure, okay? We had a theorem, if you're looking on your theorem sheet, I believe it is theorem 9.2, that says that if those arcs are the same, then JM as a segment, this chord right here, and KL, this chord, those two would be the same. That kind of makes sense that if this arc is the same as that arc, then this line segment will be the same as that line segment. So that's theorem 9.2, right? So we've got one side of the triangle here, okay? So we've got a side and a side. So we just need either another angle, another side, or a couple more angles to get our side, 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 side angle, side, blah, 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 all that good stuff, okay? So we need to figure out some more information, all right? Now, I'm going to mark this up here a little bit, okay? Let's see. Let's talk about angle L for a second, and let's talk about angle M for a second, okay? M is made from these two line segments. So M is the inscribed angle that's made up of JK. So let's say angle M inscribes arc JK, and angle L, his two sides are made up of this line and this line. So angle L also inscribes arc JK. Okay? And that's like a definition of inscribed angle. Definition of inscribed angle. I'll write it out. N-G-L-E. Definition of inscribed angle. Okay? So L and M are inscribing the same arc. So now in the next step, we can say that angle L is congruent to angle M. And that was the theorem that we just talked about. It was theorem 9.7. We'll write this down here in just a second on the theorem sheet. But theorem 9.7 says that if this arc is made by this angle and by this angle, then L and M have to be the same size, okay? So now looking at each one of these triangles individually, I have this angle and this side is the same as this angle and this side, okay? Now there's one more thing that I need to have out of those triangles. I know that side, side, side is not going to be what I use, right? Because I have two angles here. So I'm either going to use side, 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 side angle, or excuse me, side, angle, or angle, side. One of those two, okay? And one other thing that I noticed is that angle N is congruent to itself over there because they're vertical angles. So vertical angles, and we can't just call that angle N because there's four angle N's actually. This one, this one, this one, this one. So we need to name that with 3 letters. Let's call it angle JNN is congruent to angle KNN. Or, excuse me, KNL. Like that. Okay. So those two angles are the same because they are vertical angles. And then I have this triangle here. I have an angle, and a side. And this triangle here, I have an angle, and a side. So by angle, side, I have, I'm just going to repeat this proof statement over here. Triangle JMN is congruent to triangle KLN. Just like that. And there we go. Okay. That was kind of a proof that incorporated all of them in there. So a bunch of different theorems. Theorem 9.2, Theorem 9.7, a bunch of different ones. Okay. Theorem 9.8 and then 9.9 is down here. We'll write these down here in just a second. Theorem 9.8 says this. If I have a triangle that's inscribed in a circle and one of the sides of that triangle goes through the diameter. So one of the sides of the triangle is the diameter of the actual circle. The other two sides, no matter where I draw them, will always make a 90-degree angle here. So I'll kind of show you over here what that means, okay? Let me draw my diameter here. So let's say that's the center. That's my diameter. So I can make my triangle here, and it be a right angle. I can make my triangle here, and that's still a right angle. I can make my triangle here, and it's still going to be a right angle. Wherever I make that triangle, I can do it on the other side also. Here, and it's going to be a right angle. No matter where I put that third vertex over here, it's going to make a 90-degree angle. It will always. It has to. Okay. So that's what this theorem is saying, that if I have a triangle and the third side is the hypotenuse side is the diameter of the circle, then it will always form a 90-degree angle in this vertex. Okay. So find angle measures of inscribed angles. This one kind of identifies that this side goes through the center. So this has to be a 90-degree angle. Okay. So these two right here, 4x plus 2 and 9x minus 3, that's what those two angles are. And if this one is 90, then these two have to add up to be the other 90 because there's 180 degrees in that triangle. So 4x plus 2 is not equal to 9x minus 3. I can add those two together, 9x minus 3 and 4x plus 2, and that's equal to 90 degrees. Because if this is a 90-degree angle, these two have to add up to be the other 90-degree angle. Okay? So 4x and 9x is 13x. 2 and negative 3 is negative 1. And then I can add 1. So 13x equals 91. And if I divide by 13 and then x is, I don't know what that is, 7 maybe? 91 divided by 13. Yes, x is 7. Okay. They want us to find the measure of angle F. So if I plug 7 back into here, 4 times 7 plus 2. 4 times 7 is 28 plus 2. This is a 30-degree angle. Okay, that's what angle F is. Okay. And the last theorem, Theorem 9, says that if I have a quadrilateral, it doesn't necessarily have to be a rectangle, a square, it can be any quadrilateral. This one obviously is not a parallelogram, it's just kind of a weird looking four-sided figure. If he is inscribed inside of a circle, the opposite angles, like K and M, those will be supplementary. So those will add up to be 180 degrees. And then these two will also add up to be 180. So L and N, L plus N equals 180, and K plus N will have to add up to 180. Okay, that's just the way that works, okay? If it's inscribed in a circle, that it has to happen that way, right? So the necklace charm shown uses a quadrilateral inside of a circle. So we have this, it kind of looks like a diamond, all right? And I don't know if you can see in this little corner, this is a right angle. So if this is a quadrilateral inside of a circle, we know that these two have to add up to be 180 degrees. So if this one's a right angle, this one also has to be a right angle because 90 plus 90 makes 180, okay? They don't necessarily have to be the same, but they have to add up to be 180. So if this one's 90, that one has to be the other 90, right? This angle is 2x minus 30. This one is x. So those two aren't equal to each other, but we do know that they add up to be 180. So 2x minus 30 plus x has to be 180. Okay, they have to be supplementary to each other. So I've got 3x minus 30 equals 180. And if I add 30 to both sides, 3x is equal to, I think that's 210. And divide by 3, so x is 70. And they want us to find the measure of angle A. We did that. Angle A was 90 degrees. And the measure of angle B. If I plug 70 back in here, 2 times 70 minus 30. 2 times 70 is 140 minus 30. So 110. 110 degrees is what angle B is. Okay, and there's that. So opposite ones are supplementary to each other when it's inside of a circle. Here is what the theorems are. Okay, so I'll read these to you again. Theorem 9.6 is where we started. It's the inscribed angle theorem. It's kind of fuzzy, hold on. Okay, and it says an inscribed angle is half the measure of what an arc is. So I went ahead and drew my circle over here, and here's my arc. It's 100 degrees, so the angle inside of it is 50 degrees because it's half of that. Okay, I'm going to go through these kind of fast, so if you need to pause, go ahead. Theorem 9.7 says that if two inscribed angles intercept the same arc, then they are congruent. So like this blue one here intercepts that squiggly yellow arc. Same thing with the pink one here. Intersect the squiggly arc. So these two angles are exactly the same measure. They are congruent to each other, those inscribed arcs. Okay. 9.8. If an inscribed angle goes through the diameter, if an inscribed triangle goes through the diameter, then it is a right triangle. So this guy is going through the center here. And no matter what, this third vertex has to be a 90 degree. Has to be, right? And the last theorem, theorem 9.9, is if a quadrilateral is inside of a circle, like I have here, it's just kind of a weird looking, it's not even a rectangle really. If it's inscribed inside of a circle, then its opposite angles are supplementary. So I have angle 1 plus angle 3 has to be 180, and angle 2 plus angle 4 has to be 180. Okay, that's just the way it has to be. There you go. If you need to pause, go ahead and finish writing those down. But that's all I have.